Okay, let's move on to power. And I want to take you back to one slide that I had on lecture number 1, week 1, where I showed you a glass with a bear in there, right? The analogy that we use to understand the power. So power can be expressed as a true power, also known as real power, reactive power, and the apparent power. So if you look at the glass right here, real power is basically what you have in all the foam that builds up at the top. That's what reactive power is. That power is actually being wasted. And the apparent power is basically the sum, the resultant of those two. Okay, so let's explore a little more about these power. Remember that power is defined as the rate at which the electrical energy is consumed in an electric circuit. The SI unit power is watt, which is 1 joule per second. So if you are trying to calculate DC power, like I showed you earlier, there are multiple ways. You can use these equations right here to calculate the DC power. Also know that power is a function of work done per unit time. So that's where this joules per second comes in. Work is expressed in joules, T is S, so you get joules per second. And then also work is basically the quantity of the charge flowing with some potential difference, okay? And also we know that current is the rate of flow of charge per unit time, okay? So in this equation right here, if I replace W with Q dot V, and then T gets here, we know that I equals to Q over T, so this will be replaced by I and then V. So that's how you get P equals to IV, okay? So just a simple derivation, how do you get that? Now, in an AC circuit, things get a little different, okay? Now remember, and you could actually just think of an AC signal, okay? AC signal hooked up with, say, a capacitor, okay? Okay. So these reactive powers, real power, and the apparent power is actually associated with the AC electrical systems, okay, not with the DC. Now, what happened with the circuit, with the capacitive load? When we were learning about it, we realized that the voltage and the current, they reach their maximum values at different times, right? Here's the maximum value for voltage, here's the maximum value for current, so they are not in phase, okay? And I want to show you something cool over here. So if I go here, this is the same circuit as you can see on the screen. I have the voltage AC signal and I have the capacitor. If I run the simulation over here, you will notice at the top, the waveform that you see, green represents the voltage, okay? And the purple represents the current. And notice that the current and the voltage, they are not getting to their peak values at the same time. Current actually lags behind, okay? So if I stop it over here, notice here, power, if I calculate the power, look at the very right of the screen where you see these bubbles, okay? I can't do the annotation here, so you have to listen to me. You see those bubbles on the top right where the data points are? So green represents some voltage, which is going to be in positive. And if you look at the purple, which is in negative, okay? So if I calculate the power equals to I times V, the power is going to be positive or negative? Yes, folks?
Negative.
Power is going to be negative. Whenever power is negative, that means load will become a source. In this circuit right here, you have a AC signal on the left, which is 1 Hertz. On the right, you have the capacitive load, which is capacitor. Because the negative power is negative, you will see the polarity across the capacitor is that you have a positive terminal and then the negative terminal below that. That means your capacitor is now working as a source, and it will basically, if you notice, the electrons will start flowing to the left, right? And then once the power gets positive, the electrons will start moving to the right in a clockwise direction. And this will keep on happening. Once there are electrons moving to the left, that means the capacitor is discharging. And then once they are moving to the right, that means capacitor is being charged. And that's because of the power being positive and negative, okay? So let's come back here. Um, come back here. So I got that power, voltage and the current waveforms here. And I can just maybe put a legend here. So red is the current here, okay? And then blue is going to be the voltage. And then green is going to be my power that I'm going to draw now. Okay, and it's a little tricky over here. So if I look at this part here, okay, this time period over here, then both current and voltage are basically positive, right? So I'll get the power something like this, correct? All right. Now, if I look at this time period, okay, voltage is positive, but current is negative, right? Voltage is positive here, but the current is negative. So that means the power is going to be negative, something like this, correct? Now, again, over here, if I look at this time period, voltage is negative, and also the current is negative. So negative, negative, P equals to IV, negative, negative will cancel out. So the power will be positive, right? And it will just keep on doing repeating the same pattern like this. Okay, so what is happening over here? You are getting two kinds of power. One is the positive power. Positive power, which you see over here. Okay, that is what we refer to when the power is going from source to the load. In this case, it was the capacitive load. Okay, when negative power, what is happening over here? This part, negative power. That is when load to the source. That power goes from load to the source. So the capacitor will start discharging. Okay, the real power that we know is actually associated with this positive power. Okay, so remember, your real power is basically just because of the resistive load, and it can be measured as using the same equation, P equals to V squared over R. Okay, remember that V is going to be that RMS value, okay, because we are dealing with the AC signal. So, and this, what you see over here, the negative power over here, this is referred to as the reactive power, thing that is, which is wasted, not used. I want to give you another, because we have been giving mechanical analogy to understand some of the electrical concepts. So let's look at this table right here, okay? Notice you have a object right here in purple, and the goal is to move this object from position A to position B, okay? I got my hand positioned such that it's actually making 0-degree angle, okay, 0-degree angle. It's lying perfectly on the plane of the surface of the table. If I push it with some force, if I apply some force, it will actually, all of the force that is exerted on that project will actually be working towards moving this object to the point B, okay? Now, if I place my hand such that it's making some kind of angle, and I try to push that object from here to here, some of the force that I apply here will be wasted because it's pointing downwards, correct? So I'll be needing more force here in order for me to move this object from point A to point B, versus the force that will be less over here. If I position my hand such that it makes a 90-degree angle, right? So all of the force that is exerted here will actually be lost, okay? Why? Because it's pointing downwards, and this won't be able to push this object from point A to point B. And that's where the concept of the real power and the reactive power comes. So this was the real power over here, where all the force that was applied was used to move the object from A and B. Here, at this angle, let's say 45 or 60, not all of the force was used to displace the object, and therefore some of the power was wasted, and that's what we refer to as the reactive power over here, correct? And real power was the force. So what are the distinction points here? What are the key points to take away from this analogy and from what all we learned here? One thing that you always remember, then one form of power cannot be converted to another, okay? Cannot be converted to another, okay? Also, they both place a burden on the transmission line, okay? They both place a burden on the transmission line. Okay. Also remember that active power, active or real powers, both are same thing. Power produces heat, mechanical power, or light, even light. Okay. Okay. Whereas the reactive power only represents power it represents power that oscillates back and forth. Okay, another analogy to understand reactive power could be like just a pendulum. It's just swinging back and forth. It's not doing any kind of active work. Okay, also folks, remember there are a few things. Let me change the color here. So this real power, the symbol we use is P for that, okay? P, and it is, can be calculated, P equals to I square R, and it's actually measured in watts, okay? Watts or kilowatts. Then you have the reactive power. The symbol that we use for that is Q, okay? And this is represented in kilovolt amps reactive, okay? Q is calculated, the reactive power is calculated I square times X. That's the reactance, okay? If it's a capacitive reactant, then you use XC. If it's an inductive reactant, that you use XL, okay? All right, now let's now work upon the apparent power, okay? Remember, the apparent power is a combination of the two. And again, we can learn from the same phasor diagram that we discussed in the lecture number 2 on Thursday, that if you look at the resistive load, okay, that exists over here on the x-axis, right? On the x-axis, I'll say this is the real power or true power, P, okay? Then you have the reactance, which is on the y-axis, okay, depending upon whether it's more inductive in nature or more capacitive in nature. Say it's more inductive in nature, so the total reactance will be over here. This would represent the reactive power, Q, and then the apparent power will be the resultant of these two, right? So again, we can apply, the apparent power is expressed, its symbol is used as S, and they are in volt amps or kilo volt amps, okay? So this will be S. So in other words, S, if I apply the Pythagoras theorem, S equals to real power square plus reactive power square. Okay, right. So if you look at transformers, you'll probably see that their ratings are in the volt amps or kilovolt amps. So those refers to the apparent power. Okay, now let's do one example problem real quick. We have to calculate the real, reactive, and apparent powers for the given circuit. Okay, so we started with the real power. Remember this, also referred to as true power. Real power um, equals to P. This is the power that is actually due to the resistive load in the circuit. Now, also focus, guys, this circuit that you see on the top right of your screen is a little different than the one we had in lecture number 2 on Thursday. We had a series circuit where we have resistors, inductor, and capacitor. Here they are all connected in a parallel, right? So real power is only the power that is across this resistor. So I can just simply apply, VRM is already given here, 10. So P would be equal to P square over R, where this is RMS. Resistive load is 1 kilo ohm. So if I plug in the values, 10 square, resistance is 1K. So I get what? 100 divided by 1000. So that gives me 0.1 watt, right? So that's the real power. Now let's work on the reactive power. What was the equation for the reactive power? It was this right here, correct? I square dot XCL or V square over XCL. But we need to find out the total reactance first. So let's find out the total reactance. Total reactance, which will be X of T. And because it's a parallel circuit, so the total reactance will be 1 over XT equals to 1 over XL plus 1 over XC. XL and XC are given over here. So let's plug in those numbers over here in this equation. So you have 1 over 565 ohms plus 1 over 1592. And if I calculate XT, it will come down to, again, just for the sake of saving some time, I did some math already. So you will get something close to approximately 800. And honestly, I don't have a calculator. So 877, I can't find my calculator, 877.2 ohms. Okay, so that's the total reactance. And the real power, total, what was it? Yeah, the reactive power here is calculated using this equation. Q equals to V square over X T. So V square is 100, right? It was VRMS was 10, 10 squared is 100, and then total reactance is 877.2 ohms. If you do the math, you'll get 0.114. Remember, the unit will be volt ampere reactive. Okay. Now, if I need to calculate the apparent power here, power symbol is S for that. We know that it is equivalent to taking true power or real power square plus the reactive power square. So if I plug in numbers here, so real power was 0.1 square plus I had a reactive power 0.114 square, and then S will come down to, if you do the add math here, we get 0.023, and then this equals to 0.152. Again, the unit we use is volt amps here. Okay, so that's your apparent power. You also have this power factor PF, okay? And that is equals to the real power, real or true power, over the apparent power, okay? So the real power was 0.1, and then apparent power is 0.152. Now somebody needs to do the math here for me. How much is that? 0.1 divided by 0.152. How much do you get?
It's 0.657.
0.0657, right? Is that
No,
right?
it just says 0.657.
0.657. Okay. Okay. So 0.657. Okay. And that's actually equivalent to saying 65.7%, right? That means 65.7% of the power in this circuit right here was used to do an effective work. Okay. The rest of the energy power was wasted. Okay, so ideally you want it to be close to 1, but remember, those are ideal. Practically that's not possible. So just wanted to give you a true good perspective on the power related to the AC circuit system, and I went to as much detail as possible. Remember, this was the capacitive load. Same thing would happen if I change it to inductor, right?